Okay, so I think we can start now. Welcome again to everybody and thanks for joining our technical webinar from Heraeus Next Sensors. For those who don't know me yet, my name is Lisa Würke. I'm responsible for the marketing and communication activities, and I will support the team in regard to your questions. Our speakers today are Charlotte Klemen and Martin Bleifuß from Application Engineering team, who will guide you through the presentation and are open for questions. So before we start, on the next page, I want to introduce you a few general information. The webinar is planned to have a duration of 1 hour, which includes a Q&A session afterwards. Please note our session today will be recorded and used for internal trainings and will be available for you afterwards. Regarding the settings, all attendees are muted by default. If you have any questions, please address them into the chat box, which you can see on the right-hand side. Questions here will be managed from my end and included into the presentation directly or collected for the open discussion round in the end. Due to data protections policy, we are not allowed to address any specific individuals to keep you anonymous. If there are detailed questions, please come back to us afterwards via mail or phone. Please make sure that your audio works. Our recommendation here is using the headset. Another option is to dial in via phone. You've received the recording number by invitation mail. And now I hand over to Charlotte Klemen, who will start with the webinar. Thanks.
Yes, thank you, Lisa. Also, a very warm welcome from my side. We are part of the application engineering team of Heraeus Next Sensors. And today's topic of the webinar will be the installation of temperature sensors and the impact on performance. Yes, so I'm really looking forward to give you a deeper insight into key points in temperature sensing. And I'm also looking forward to your question and the exchange afterwards. So yes, let's get started. So here as a quick overview, our agenda. So what we want to cover today. So as an introduction, I will share with you some exemplary installations of our temperature sensors. And then I'm going to highlight some performance factors that are influenced by the installation. Here I'm going to point out in step 3, 4, and 5, different performance factors and explain their impact and also how those performance factors influence each other more into detail. So we're going to talk about the performance factors, for example, the response time, the installation resistance, thermal expansion, the humidity resistance, the shock and vibration resistance, and also the temperature of the application itself. And last but not least, Martin will, in order to round off the webinar, give you an overview or an idea of different housings. Yes, but first of all, as an introduction, and so that you guys know who's actually talking to you, Martin, since you're my boss, please go ahead.
Yeah, thanks a lot for the chance to introduce myself. My name is Martin Bleifuß. After the diploma in mechatronic and some years in the heat treatment industry, I joined Heraeus in 2005. Over the years, I worked at Heraeus Electronics in different positions, and in 2016, I moved to Heraeus Next Sensors, and I started or built up the application engineering team there. And I hope you enjoy the webinar now, and I hand over again back to Charlotte. Thanks.
Yes, thank you, Martin. Yes, my name is Charlotte Klemen. I started my bachelor degree in economical engineering in cooperation with Heraeus in 2015. And then during my master degree, I was working as a working student in the sales department for Heraeus Precious Metals. And then I changed internally to the application engineering team of Heraeus Next Sensors. And there actually I started this year in the beginning my first full-time position. And yes, now I'm mainly responsible for the technical support of our customers and also for technical trainings internally, externally. Yeah, actually just like this one, what we got today here. So don't worry, we'll now turn off the videos. Okay, so let's start. Yes, let's start with an exemplary overview of typical installation of temperature sensors that belong to our product portfolio. So you can see here different temperature sensing examples for the e-mobility sector. So we have here on the left a charger block, for example, on the middle top an e-motor example, on the bottom the power electronics, and also the battery application. You can also see on the top right different house sensor elements which match to different applications. This is really just a rough overview. Martin will bring this down to a round figure and he will show it to you again at the end of our presentation. So here you can see now different factors that contribute to a good performance of our sensors and that are also influenced by the installation of the sensor probe. So we're going to talk more into detail about the heat conductivity, or as we call it, the response time, about the insulation resistance, the thermal expansion, the humidity resistance, the shock and vibration resistance, and also the high temperature stability. You can also find these terms also on our data sheets, for example. But let's start with the first two, the response time and the installation resistance. Why both? Because both are influenced by each other. So let's start with a definition of the response time. The response time is the time a system takes to react. So this is a really, really general approach. So when we talk about our sensor element, it's the time the sensor takes to detect the right temperature. So we obviously want to have a fast response time. So when we talk about a Planck sensor element, you can also find there the data concerning the response time on our datasheet. You got to say that in general, the thin film technology, so the technology that we use for our platinum sensors, have all in all a really good response time. But let's take now a closer look to the house sensor elements. So you can see here an example in the pictures on the top on the left. Here it depends really on the way of mounting. So I want to point out two main factors that influence the response time. This is on the one hand, the diameter and the wall thickness, and on the other hand, the materials. So by material, I mean the material of the housing itself and also the filling material. But let's start with the first factor here, so the diameter and the wall thickness. All in all, you can say that the more material you have around the sensor, the slower is the response time. So you have here a drawing example, and you can see directly there's a lot of material around our sensor element. So that would result in that case in a bad response time. So now we always like to use models in order to explain the reality a little bit better. So let's imagine you are wearing a winter jacket because in winter you don't want the cold to get to your body too fast, right? So this would represent a slow response time. If you would now wear a t-shirt in winter, your body temperature would cool down like really, really fast. And this would represent a fast response time when we talk again about our house sensor element. So here you can see again at the here in the drawing that there's less material around our sensor element. So you guys say in general again, to achieve a better response time, the diameter should be small and the wall thickness should be thin. So the next factor is that influence the response time is the material. Again, a little drawing here of a house sensor element. And we have to say that even for thin film technologies, there would be a bad response time if the tube would be only filled with air and not with a special filling material. So we insert here a filling material. This is an example from the conductive paste. In green, you can see that here, and that conductive paste improves the response time. You always have to take care of so-called air holes. That would also decreases the performance and response time. And we also have to say that the heat conductor, that the conductive paste is still not an amazing heat conductor, but it's definitely better than air. So the example we got here now in the picture. So I already referred to that you can also change the material of the housing. So let's do this now. So the housing also influences the response time. So for example, a metal is a better heat conductor than, for example, glass or whatever. So when we talk about the term response time, always terms like T05 and T09 come up. And you can also find those terms on our data sheets again. So in order to explain those terms, let us ask ourselves the question, how much time does the sensor take to react to an environmental temperature of 100 degrees Celsius? I just used the example of 100 degrees Celsius because it's like really, really easy to calculate, and you will see directly what I'm referring to. So let's take a look at the graph. You can see in the x-axis the time in second that the sensor takes to react, and the y-axis, the temperature in degrees Celsius. So let's have the example with an M222. The M222 is like a really standard sensor element from us. Yes, when we now take a look at the term T05, it would take, in this specific example, the sensor 0.05 seconds to detect 50% of the final temperature. 50% is in that case again a 50 degrees Celsius. And here the same for the T09, that would take our M222 0.15 seconds to detect 90% and therefore a 90 degrees Celsius of the final temperature. So the data that you can see here stands for the response time in a water current. You can also find data on our data sheets for air current, for example. It's also important to know that you can't transfer the data directly to the response time of your application. So this is really just a point of reference, and the response time depends on many other factors. So let's come to the next definition, the installation resistance. The installation resistance is the resistance between the housing of a sensor and the sensor element itself. So it's really the resistance against an outer electric current. So here it's the installation or the protection of the sensor probe must follow the end application and also the mission profile. On the bottom, you can see a rough sequence of different housings. Just as an example, here the plastic housing on the left has a better installation resistance than, for example, a metal housing. But we will have here a closer look. Yeah, and again, just like we talked about already concerning the response time, several factors are responsible for good performance in the installation resistance. So let us ask ourselves the question, how can a bad installation resistance emerge? I have like 3 answers to that question. First of all, a bad protective insulation material of housing and potting. This is the point I was already referring to in the last slide, and also Martin will go over this again. The second point is by a too small distance between housing and sensor, and also from an electric conductive material between sensor and wall, like a liquid or humidity, for example. So here you can say that, yeah, humidity is always harmful for an insulation. You can see here now a picture on how we measure the insulation resistance. This is a ball bath, and I want to give you the recommendation here to do the testing in the ball bath with a house sensor due to the risk of measuring faults by testing a Planck element. So on the top, you see the testing with a Planck element, and on the bottom with a house element. And this is due to the fact that you can see that already in the picture, it's hard to have an exact positioning of the sensor in the ball bath, so the wires of a Planck element could reach into the bath. And also the covering glass is partial porous, so it's not fully insulated, and that could also lead to an electric shortcut. So just as a recommendation, the testing should be done with a house sensor element. So when we now bring both performance factors, so the response time and the insulation resistance together, we can see that the factors are contrary and that the factors are influenced by each other. So we need to balance both of them. And yeah, you've seen that before already. So we always like to use models in order to understand the reality a little bit better. And that's why we put here Manuel Neuer, actually. Manuel Neuer is the German soccer goalkeeper, and he's wearing gloves in order to protect his hands against the ball power. And this would stand in our model for the insulation resistance of our house sensor element. So on the one hand, he needs the protection against the ball, but on the other hand, he also wants to have a good ball control and a good sensitivity in his class. And that kind of represents a fast response time of our sensor element. So for example, if Manuel Neuer is now wearing really thin gloves, that would mean a good sensitivity in his class, so a good ball control, but also a bad protection for his hands. And this is comparable to a little housing material surrounding our sensor. So what you can see here in the picture. And that would represent a good response time, but also at the same time a bad insulation resistance. But how to balance now the characteristics of the housing and therefore the performance factors in a right way? So take a look at the graph here. You can see here how the housing, you can see the housing also on the bottom, some pictures there, contribute to the different performance factors of the response time and the insulation resistance again. And we need to find an optimum that fits to the special application. So again, an example, we have application A and application B here. Take a closer look on application B. For application B, the sensor is in need of a really good performance in the insulation resistance. So that's why the orange graph is here like really high. And therefore, we need to accept a bad performance in the response time. That's why the graph is in green and very low. So this is really what we mean by balancing those performance factors. You always need to fit your installation to your application. Yes, but now enough from those two performance factors. I'm now going to pass on to my colleague Martin. He's going to tell you a little bit more about the next 3 performance factors: thermal expansion, humidity resistance, and also the shock and vibration resistance. Please, Martin, go ahead.
Yes, thanks, Charlotte. Yeah, the problem with the different factors is you optimize one, and on the other side, you reduce performance on another factor. And if Charlotte spoke in the slide before from a bad behavior, it's only in comparison to a different insulation. That means bad is not really bad. Bad is compared to a not covered or not protected sensor. Bad means slow in terms of response time, for example. That means, on the other hand, there is no optimum possible. Target must be to find a best compromise between these factors. Let's go to some examples. We have to cover and to protect our sensors typically. And if you use the wrong materials, it leads also, or could lead at least, to some trouble. That means in the top picture here, you see a SMD, surface mount device sensor, which is mounted, like a bridge between two substrates. In the most times, this could be a PCB, DBC, or maybe also between two stamped parts. And in that situation, you have insulation around it here in green. And if you put now heat to that system, which is typically for a temperature sensor, then you have different thermal expansions of the metal part here and the metal part there, and the potting material has a different heat expansion, and also our sensor has a special heat expansion. And if you combine now some epoxies which are quite different compared to metal and ceramic, then you can kill your complete system. Even if you think all properties are good, that means you have a fantastic insulation, you have a real good adhesion in the situation of the mounting, everything looks really fine and good. But after heating up and cooling down, heating up and cooling down, after some cycles, you could destroy that system. That means you have to take care, if you want to cover your material or your system, you have to take care about the different materials. Yeah. And on the lower picture here, you can see a different application, which is much more smooth in terms of interconnections and thermal expansion. Here we do, more or less contact only for the thermal conductivity, and we have separated electrical conductivity on the top side of that SMD part. This is only an example. And if you have here in that system now a thermal expansion after thermocycles, for example, then you are much more flexible because you have a wire connection to this area. This is compared to that sintered, soldered, whatever connection, quite flexible. And this is the reason, if you look from the outside on that material or on that system of that probe, it looks similar or looks even same. But if you look a bit closer into the system with an X-ray, like shown here, you see that there is a big difference, which leads to a different performance. Yeah. And this is what you have to take care if you think about potting, mounting, and so on. This is only one example. Second example is an example for humidity resistance. If you look on the left side, you have an idea which is a M-type, a typical thin film sensor, and it's fully covered with glass, which speaks for a very, very good yeah, humidity resistance. That means it's really, really good sealed. And on the right side, you have also a good sealing version with a PDFE melting and shrinking tube combination. Both are very good in sealing, but they have differences in terms of temperature resistance. Here you see the material or the system which is protected by a shrinking tube only has a lower temperature performance compared to the glass version. But on the other hand, you could not use a glass version because the material glass is very brittle. You could not use a glass or brittle version in a system which is driven by high vibrations or strong vibrations or in general mechanical attacks. Yeah, this is the reason why we said, okay, both systems are really good for humidity resistance, but you can't exchange these systems. That means the glass one is used here in a lung ventilator. Our customer Traeger here is using that to control the breath and the temperature of the breath, which gives an indication of the health status of the people or the man. And on the other side, you want to control an electric motor, which is completely different application for sure, and you have to take care about the environment, which is much more rougher here. This shock and vibration resistance is also not a single parameter. It's also always taken into account into a complete picture. That means if you take this really good version I showed you before with that shrinking tube version, which is for harsh environment, yeah, you can use it for these applications, but this has a limitation in terms of temperature, which I highlighted before. And if you want to have a suitable version for higher temperatures, you have to change again your cover, your protection. And in that example, you see protection which withstands temperatures up to 550 degrees, for example. This is here a ceramic housed element. It's a ceramic tube, it's a ceramic filling, and our sensor is potted in. But on the other hand, it's again a bit more brittle than the version on top. That means you could not use this version in an electric motor, for example. Yeah, sealing is also not so good compared to that shrinking tube version. And this is the reason why we have to say it's not possible to find the optimal solution for everything. You have to think about your application and the parameters which will attack our sensor. Speaking about high temperature stability, there are also some different factors which we have to take care about. That means if we begin on the sensor level, we start for sure with different layers. Our sensor itself is typically made of aluminum oxide, and there is a PT meandration, our platinum resistance on top of that layer. And then we have different glass layers with different functions. One is only for covering, sealing, and then you see the blue glass, which is a fixing drop for our wires. And for sure, we use different glass types for different applications. That means low temperature sensors have different glass layers compared to H types, which is a high temperature sensor. And if you made the wrong choice in the sensor element itself, it could also lead for sure to some trouble in the application. But this is only the sensor sandwich system coming to the interconnection or to the connection technology. We see here wired types, which have wires for the connection to a cable, to a PCB board, for different ideas of connecting. And these connection technologies have also different temperatures as a kind of an application windows in the background. Means we have wires which are optimized for soldering because our customer wants to solder, but then you have a limitation around 150 degrees. Others love to use a welding process, which could be laser welding or a different welding type. And these wires are different compared to solder optimized wire type. And if you use welding, your temperature goes up in a different range. And we have also wires which are optimized for deformation, which is in the end crimping, and then you can put some connectors or other wires with a deformation system and connect these wires to this cables and maybe also connectors. This is also possible, but all these different wires are optimized for different connecting technologies. On the right side, we have these connecting types, described with soldering, welding, crimping, sintering, but we have also the special types for surface mount devices, the SMD types. And these types, you can see directly, they have no wire. That means our customers use these SMD types to put it directly on a board. That means with an SMD type, you can solder the SMD sensor directly on a PCB. And if you need higher temperatures, because a PCB is typically limited up to 150 degrees or a bit higher, but not over 200 typically, then you have to move, if you need higher temperatures, then you have to move to different SMD technology, which is sintering, silver sintering. In that situation, we use the complete backside for the sinter process, and this sintering is only for the heat transfer, not for the electrical connection. Means we need additional wire bondings on the top side, which is also done by our customers. And you can see here you have the layer system, the sandwich system, which influence our sensor. We have the connecting technology, which influences our solution in the end. And again, we have that housing. And the housing topic, Charlotte gave us a nice overview. Here are some different examples where you see how these temperature steps could be overjumped. On the left side, you see again that application in the E-motor. You have here that shrinked wired sensor element, which has really a good performance in terms of sealing, in terms of vibration and resistance in mechanical topics. But on the other hand, there is a temperature limit, which is limited up to 250 degrees. If you need higher temperatures, example for chemical process equipment, petrochemical devices and so on, there is typically a different housing necessary. You can't work with these cables which are melting at temperatures over 250. You can't work with that shrinking tube, which is limited up to 250, and so on and so on. Then you can switch to a different housing again, which is a ceramic tube filled with that ceramic paste, and you put in our sensor. You have to take care about bubbles and air holes like Charlotte described before. And if you make everything proper, make a nice connection, you can put it into a probe like that, and you have a good solution which works up to 550 degrees. If it comes to temperature ranges up to 1000 degrees, which are typically for combustion engines in our automotive world, then we have to work with complete different materials. Yeah, that means we have different housing materials, which are high nickel based alloys. They have to be very good sealed with very special welding processes, that there is everything really nice connected. And if you have now these connecting wires here, they are protected in the tube with the mineral insulation, which is really special to handle that. But this is the only chance to withstand 1000 degrees, yeah, with a good enough electrical insulation. Yeah, that means you see there are different temperature windows where the sensor system must perform, but the solutions are even different. Yeah, and if you compare these, or if you say, okay, then I take the best one and use it for everything, yeah, looks like a good idea, but you have to do, or you have to invest a high effort for a solution like that. That means, yeah, the complexity is increased, means the costs are increased. That is, on the other hand, yeah, a very good solution, but you don't want to pay this solution for all applications you can see on the left side. This table shows in one slide, or we try to show in one slide at least, that the solutions will not cover all factors. And you have to ask very precise for the application and the influencing parameters. That means Charlotte spoke from a mission profile. You have to take care what you want to do with that sensor probe, or what your customer wants to do with that sensor probe. Yeah, otherwise you could easily do a failure by searching for the right materials for covering, insulation, connecting wires, and so on. That means you have to take in account always the mission profile. Yeah, remember in that slide you have to remember the slide 12 from Charlotte, where the goalkeeper gloves are shown, and there you can easily understand a good protection, yeah, is nice to protect your hands, but it's bad for the sensitivity, for the sensitivity for the ball in the in the slide 12, but in that situation for the sensitivity of the temperature. A well-protected sensor is typically a bit slower than a not so well-protected sensor. And this is the reason, yeah, why we have to say it's not possible to find the optimum. I think it's good to have the best compromise, yeah, but this is hard enough to find out which is the best compromise. You have to take in account always the response time, insulation resistance, and the protection. These are the three main factors we have to think if you develop or think about a new combination of materials. The high temperature probe, for example, shows with high effort, unfortunately, high costs. You can shift a bit the limitations here on the right side. This is this HTP version, which is a high temperature probe. There are a lot of pluses, but you have to pay a lot of effort into that system. Means it's a cost-intensive probe, and it's not helpful to have this cost-intensive probe for all applications in lower temperature ranges. But what you can see, there is a trend of the pluses here. The higher the temperature, the worse is typically the heat conductivity. The heat or the temperature stability is also in that area decreased compared to the right side area. compared to our last webinar, we had now a bit more time for the discussion. Last time, yeah, we put a lot of information in our 1 hour session, and yeah, this leads to a bit less time for discussion and for the question and answer session. This is the reason why we shorten a bit our more or less content today. But what I want to show you as exemplary installation in the end, these types which we saw before. We have here a PCB type. That means we have an SMD mounted on a PCB, and this is wired in the end. You see these red wires here, and then we put it directly on the backside of a connector for an e-charger, e-mobility charger, yeah. And then you have, an optimized heat transfer, because the sensor is very, very close to the heat source, because in that area the heat will increase because of an connector resistance. And you can also use a different mounting device for the same application. You can put a hole in and put a well-insulated sensor in that hole with a kind of an transfer or insulation paste or heat transfer paste, which leads to a comparable result. And these are only mounting examples. In the middle area of that slide, you can see that shrinked wire sensor, which is typically used for e-motor windings at the moment, very popular for the e-mobility approach. But we see also a lot of different applications where this solution is really often in use, because this is, as I said before, really a robust, quite flexible, and not really expensive solution. In that area, you see our surface mount devices. In that example, you see a SC sinterable chip, which is suitable for higher temperatures. Our chip withstands temperatures more or up to 500 degrees, but because of the packaging technology, and here's our sensor, here is included the aluminum wire bonding technology, we have a limitation up to 200 degrees at the moment. But this helps our customers to go to the next level in power electronics, where higher temperatures are needed. That means this is a switch from 150 degrees up to 200 degrees. On the right side, you see some housed elements for more or less white goods. These are typical oven sensors, which are used in pyrolytic ovens you have at home. And I think it's a good idea to have a nice temperature control in that white good materials, because if you want to clean your oven in the night, I think it's a good idea to have a well protected temperature process in that to protect yourself and your house, for example. And on the right side, you see here a SMD, a typical soldered version, which is the white point here, compared and combined with an flexible polyimide foil. And the backside is, for example, could be covered with a self-adhesive tape. That means you can use it like a sticker and connect it on the connection area here with a plug, and you have a sticker which is able to detect directly the temperature where it's sticked on here. A lot of people think about these solutions in battery applications, but I think in general it's a very, very flexible solution. For sure, also here you have to take care which temperature ranges must be withstand. That means, what is the mission profile? You can believe with a plastic foil like that, you are limited again in the temperature, and you can't work with a solution like that up to 500 degrees, for example. Yeah, this is only a rough overview about some different applications, but I think if you have very, very special questions, you can use the time after the meeting, after the training, by sending us emails, but you can use also now the time for some questions, and I invite you to highlight your questions, and Lisa will take your questions. Maybe she collected some of them during the time, and we try to answer the questions now. Thanks for your attention, and hopefully this will help you for your next discussions internally and also with customers, and helps you also by choosing the right system. Thanks a lot.
Okay, thanks Martin, thanks Charlotte for the presentation. So please address your questions into the chat box now. So far we do not have questions, but if so, please use the chat box on the right-hand side.
As I said before, if you have very special questions which are not for an official discussion here, no problem for us. You can ask us directly also later. You can use the chance to discuss in detail some topics. If it's necessary for you, we can also make an NDA before discussion of some solutions. And yeah, we are open not only here in that time slot for Q&As. We are open in general to help and support you for your hopefully best solution. Yeah.
So one question arrived.
Okay.
Is the glass encapsulated version generally available?
Yeah, this is typically an example where we show what is possible. We had that in our standard portfolio, but we removed that from our standard portfolio some years ago. This is an example to say how we can work with glass, we can cover it very well, and it has also some advantages in performance, especially if it comes to sealing and so on. But if you have really a good idea for a good application for that, and the numbers will fit, that means the amount, the quantity over the year is high enough, we can more or less rethink our situation, and could come back with a solution like shown before. Yeah, but typically it's possible, but it's not in our standard portfolio at the moment.
Okay, several more questions arrived. The next one, is the heat conductivity for metal and ceramics really smaller compared to plastics?
Yeah, also a good question. We have different plastics, and we have to take care which plastic we use. And on the other hand, if you have a metal housing, then for sure you have typically a very, very good heat conductivity. Unfortunately, yeah, if you don't use a paste, which is the insulation electrically in between, then you have a shortcut. That means you have to think about the jacket, what Charlotte described before. If you use a metal housing, there is typically not only the sensor in. That means you have to take care about potting. If it's plastic, if it's silicon, if it's a paste, a ceramic paste, whatever. And this is more or less in the end the factor who is responsible for the heat transfer or the heat conductivity in that solution. That means it's a general description, and you are completely right. You can't say easily that a metal house sensor is better or worse compared to a ceramic one.
Okay, the next question.
Depends on wall thicknesses and so on. Sorry. Yeah, depends on wall thicknesses and so on. Yeah, sorry.
Okay, next question. Why is the PCB version used for fast e-vehicle charging instead of the M series elements?
Mm-hmm. With that PCB version, this is only one example. We have also M types in that application. It's mostly customized, and we can't show all applications because, yeah, the single solutions are sometimes really customer solutions. That means they are protected by IP, or we are not allowed to show it. But in general, you have to take care, especially for that EV charging application, that there are high voltages which will be transferred, yeah, in a short time. This is the core idea of fast charging, yeah. And if you have these high voltages, you have to have a very good insulation resistance. And this is the reason why it's sometimes really helpful to work with the PCB, which gives you electrical insulation layer in between to protect the sensor for an overvoltage, for an overshoot, and on the other hand, being fast enough or good enough to get in a response time which is okay for this application. If you work with the M type purely, then you have to protect that M type. You can't put it directly on that metal part of that pin on the backside like we showed that before, because then the insulation resistance, the electrical insulation resistance is too bad. But what you can do is you can think about additional layers you have to add and things like that, and our customers are doing that. Yeah, that means for sure there are also M types in use for charger plug applications.
Okay, the next question in German, but I will raise this in English that everybody can understand. What are the reasons for the increasing tolerances of the sensors with increasing temperature?
Mm-hmm. It's not really easy to answer. If you have higher tolerances, if you have higher temperatures, the complete system will expand. That means the higher the tolerance, the more elongation you have in different materials. That means it has an impact on the resistivity. That means on the resistance value of our sensor, not on the resistivity of the platinum material itself, but on the length of the meandration, for example, which has then an influence on the meander itself. Then you have sometimes a kind of a bending of the complete system, and if you bend our sensor, it's more or less than like a strain gauge. That means these bendings impact also the resistance which you can measure, and this is for sure harder to overcome at higher temperatures, because the effects of thermal expansion and also the effects of, I don't want to call it diffusion processes over in high temperature applications, but there are some interactions between the materials at higher temperatures, and you cannot jump over the physics. You have to reduce then the accuracy to say, okay, we are then maybe in a standard B or in a standard 2B tolerance if it comes to higher temperatures. This is only in respect to the materials in use. You cannot, or you could not typically have the same accuracy at 1000 degrees compared to a solution which works at 300 degrees, for example. Hopefully I could answer this question. If not, don't hesitate, re-ask or ask again.
So far, no more questions.
Okay. By the way, also in the normation, there are temperature levels, and they are directly connected with the accuracy. That means, if you need a tolerance class A, for example, the performance is limited typically in the normation up to 150 degrees. And if you go, I think over 550, I'm not sure at the moment, then the normation will end, and you have to, talk to your supplier to ask what is possible and what not. It depends then really, really drastically on the combination of the materials in use. And you don't speak about the sensor element only. There are a lot of influencing factors we showed you before, which are at higher temperatures much more, or they have in higher temperatures a much longer lever.
Okay, one more question.
Mm-hmm.
Could you increase the sensor working temperature using a housing, or it works in the other way?
Yeah, in general, you need the right sensor. That means we spoke about the sandwich system. That means the sensor must withstand certain temperatures. If you use the wrong classes, the wrong wires, the wrong interconnection technology, you can do with the housing whatever you want. You will not reach the performance. But if you choose the right sensor with the right wires, with the right connection technology, the right class layers, and so on, then we can use the suitable material for the housing, and then you can increase for sure the emission profile, the application temperature. But for sure, if it comes to temperatures over 1000 degrees, the insulation materials are the limiting factor, not typically the sensor itself, because the insulation materials have a strange behavior. The higher the temperature, also an insulation material will lose the property of insulation. That means with higher temperatures, a lot of materials they can then transport current and voltages. That means the insulation power is reduced. That means it's not really a limiting factor for the sensor, but a sensor without housing is nothing worth. And in the end, you must find the combination of all.
Okay, so no more questions. Then I would like to thank you for joining our webinar today. If there are further questions afterwards, please address them via mail or phone. We are pleased to reply directly. And I wish you a nice day and see you soon. Thank you.
Yes,
Thanks
also
for your
big thank you
attention.
from my side.
Yeah, thanks also from my side. Thanks a lot. Have a nice day. Bye.
Bye-bye.